All right, this is a lecture for Chapter 2 of Chemistry in Context, the second lecture. I titled this part Dangerous Things in the Air. So in the first lecture we looked at what's normally in the atmosphere, and now in this part we're going to go ahead and look at other things that are in the air that we don't necessarily want there. So carbon monoxide, ozone, which is unhealthy to breathe, sulfur dioxide, which comes from burning coal, among other things, and creates an acid when it reacts with itself and with oxygen and with water, and the different nitrogen oxides, especially like the nitric oxide, which is NO, the nitrogen monoxide, which is pretty toxic and comes from high temperature combustion of nitrogen, oxygen, and other things. Lead. Here in Joplin, Missouri, where we are, there's quite the history of this because we had Eagle Pitcher, we had a lot of lead mining in the area, we had lead smelting, and that put vaporized lead into the air. And Eagle Pitcher in North Joplin left a lot of lead that then precipitated out of the air into the soil. And if you paid attention to the news about the last 20 years or so here in the Joplin area, a lot of lawns in North Joplin, the EPA came in, scraped off 3 or 4 inches of soil, replaced that with fresh soil so that the lead is not getting into, is not getting ingested into dust, like dust, and ingested by kids and things like that, and giving them lead poisoning. So there was a lot of lead here in the area. If you go out to where the chat piles are and you play around in those, you're still going to get a lot of lead dust that's there. And that's why we have been spending a lot of money and effort to clean those up and cap them off with soil. Then there's particulate matter, which could just be dust, or it could be smoke, or it could be viruses, we'll talk about a little bit. Could be tiny drops of liquid. And those are, I learned this when I looked in this chapter. This isn't something I knew before I read this chapter. They're classified as PM10 or PM2.5 based on their sizes. So 10 being less than 10 micrometers, that's a micro means 10 to the minus sixth, and 2.5 as in less than 2.5 micrometers. And those smallest of those can actually get inside your cells. The larger of those are going to make you cough them out, and you've probably gotten a bunch of dust where you've breathed, and then you've blown your nose and it comes out with a lot of dust. So some of the larger particles will just come back out, but the smaller particles can get inside your cells. There's always going to be some particulate matter. You can see dust in the air when a sunbeam is coming through the window and you can see the particles of dust in there. So there's always something. You can't get rid of it 100%. The issue is that it's not necessarily toxic unless it's a larger amount and a larger time. So the exposure that you have to particulate matter is important. So how much there is, and also how long you're exposed to it. And this, you've heard this, the dose makes a poison. Like pretty much anything is poisonous. Water is pretty non-toxic, but if you drink too much water, you will throw off your electrolyte imbalance, you can have nausea, you can have vomiting, you can drink enough water to make yourself sick. So anything can be poisonous. Oxygen itself, we need to live, but if you live in an environment of 100% oxygen, that's toxic because oxygen creates free radicals, very reactive, and can make you sick or kill you. So even things that we think of as necessary for life can be toxic. Similarly, things that we think of as toxic, like lead, you can have as long as they're in tiny enough amounts, you won't see any consequences from that. So it's a different level of toxicity, but there's always some kind of level, hence this quote. All things are poison, and nothing is without poison. The dosage alone makes it so a thing is not a poison. It's just that the doses are different. So we, as in regulatory agencies, have quantified how much of certain pollutants are acceptable. So if you think about carbon monoxide, quite toxic, only 9 parts per million is considered too high if you're exposed to it for like an entire workday. But you could be exposed to as high as 35 parts per million if it's only for an hour. So it depends on the level, and it also depends on the time that you're exposed. Here's some particulate matter. Notice the larger particles you can have a higher concentration of before it's considered toxic, and the smaller particles a lower amount. And this is over one day, and this is over like permanently. So if you lived in a place where it's always this much, then that's considered toxic. But if it's just a short period of time, you can handle more. So if you could look at lead, we don't even have that in parts per million because it's so tiny. It's 0.15 in micrograms per cubic meter. So if you look at the conversion between this column and this column is about 10,000 times bigger than this column. So if I divided this by 10,000, right? So 0.15 divided by 10,000, I'll just do that. So that comes out to 1.5 times 10 to the minus fourth parts per million, which if I want to change that into parts per billion, I'm going to multiply that by 1,000, and I would get 0.15 parts per billion. Super tiny amount. So like less than a drop of lead in a whole swimming pool of water is considered a toxic level of lead. So you can, after our discussion, you should be able to answer these kinds of questions. And I will let you think about those and see if you couldn't answer those kinds of questions for a homework assignment or for a quiz, for example. I thought this was a good time to talk, since we're talking about particulate matter. What do people do when they live in places that have a lot of particulate matter? Like, where's this picture? Like this, Beijing. They end up wearing N95 style masks to prevent themselves from having to breathe that kind of particulate matter. Well, what are we doing right now? We're wearing masks to prevent ourselves from getting the coronavirus infection. So just like particulate matter, there's a range of amounts that will or will not cause an infection. So you can't really say, masks work or masks don't work. Like, I see this all over the place on social media. People say masks don't work. Well, it's not that they don't work. It's that there's a range, right? So how many virus particles do you need to have to get an infection? Again, that's a range. It's going to depend on how healthy you are and how far you breathe them up into your passages, and how you're feeling that day, how old you are. But if you only get, let's say, less than 10, you're probably not going to get infected. If you have more than 1,000, you probably are going to get infected. And then in the middle, we don't really know. So there's no guarantee that you'll get infected, and masks don't guarantee that you won't get infected, but they can reduce the number of particles. Here is a graphic from a scientific study where they showed which kinds of particles can be blocked by masks. And here, here's a person not wearing a mask, and they're expelling a lot of water droplets, and the larger the water droplets are, the more virus particles they have. Whereas you might have 1,000 viruses in just one particle of this size. Well, most of those particles don't get through the mask. This might be the actual size of the virus, like 0.1 micrometers, and some of that might actually get through. But if not very much of it gets through, you can reduce to a lower exposure and reduce the risk of transmission. And if you want to see if masks work, I just went yesterday and pulled up some data about different countries that have mask mandates versus countries that don't, like ours. This is actual data from yesterday. You can see this is still all the way up to January of 2021. Australia, in the whole country, they've had 22,000 cases total, but the day before I collected this data, 1 case. In New Zealand, no cases. And in the United States, 188,000 cases. You don't need to have 100% effectiveness from a mask to make the pandemic end. You just need to reduce it so that each person who's sick infects fewer than one person. So like for every 100 people who are sick, if they only infect 90 people, then eventually 90 becomes 80 and 80 becomes 70 and eventually it goes away. So what kind of mask is the best? You might have heard about these N95 masks. They're called N95 respirators, and those are certified to remove 95% of particles of around 0.3 micrometers. It works by electrostatics, so those particles will just kind of stick to it, kind of like those Swiffer things that go on a dust mop and the dust sticks to it. It's the same kind of thing. So then it turns out that the coronavirus, the SARS-CoV-2 virus, is actually smaller than that. So does that mean masks don't work? Again, not necessarily, because first of all, it's going to stop some of those particles, even if it's not 95%. And secondly, most of the virus particles are in these water droplets that are much larger, and those do get stopped by the masks. So masks help, right? You can't say they work, or you can't say that they don't work. You can say they help. That's the best we can say. A cloth mask, which is what all of us have been given for free from Missouri Southern, some nice ones with a lion face, they're pretty cool. They are less effective, and the more layers that you have, the more effective it is. So there's, here's a study, I'm not gonna, but if you wanna go look at this study and the YouTube video, Duke studied 14 different types of masks. If you just have like a one layer of cloth, like a bandana or a gaiter, it turns out that that is no better than no mask at all. But if you fold it over so that it's like 2 layers or 3 layers, then it becomes more effective. You could even wear 2 masks, as long as you can still breathe, right? You need to be able to breathe to live. The rest of this lecture is just showing you some historical concentrations of pollutants, and that in the last 20 years or so, that those have declined in the United States. That's due primarily to better regulations of pollution emitters such as industry and vehicles. Here's a picture that shows air quality. Notice Kansas City is the nearest big city, pretty low, compared to Los Angeles, super high. They have a lot of those inversions in Los Angeles and a lot of vehicles, tons of vehicles, and they just get tons of smog. Smog, which is a smash up of the words smoke and fog. So you have smog. So you can use the data from this annual report and answer some questions. There's a way to measure the air quality index, which is related to the amount of particulate matter, and then you can do that map, a color-coded map. And there's a color-coded map that shows the air quality over California, Southern California, over some days when there was a fire in 2018, known as the deadliest wildfire, and you can see that some of those days it was really very unhealthy to breathe. This year, you might remember, well, in 2020, you might remember lots of wildfires in the Pacific Northwest. I have friends who lived out there, and they had to wear masks in their own homes. A lot of the places up there don't have air conditioning because it's never that hot. And so they just had to either suffer by keeping the windows closed and being hot. I even had friends that bought a box fan and then got air conditioner filters put behind the box fan and then just turned the fan on to just kind of filter some of the air inside their house or apartment so that they could, breathe without getting a headache. So air quality, certainly important, and natural sources like wildfires are probably worse for the air quality than even industrial pollution, although there's some evidence that wildfires are a lot worse because of the dryness and heat that we have in recent years due to climate change. All right, that's the end of the second lecture. Only 15 minutes. Cheers.